I was thinking about the example of sort of the difference between worrying about an algorithm as a sequence of actions that you take versus an algorithm being a sequence of places that you are, states that the algorithm is in. So I was thinking of this example. My aunt gave me these instructions. Go straight until you hit the McDonald's and turn right. And then go until you hit the Wendy's or whatever. And I was following the instructions quite well until I got lost, and I realized that I was in the wrong state. Right? If you go far enough in America, you will hit a McDonald's and turn right. So how does this relate, other than being a funny story? I'm not sure, but if you know where you are, the state of the computation, you focus instead of focusing on instructions. Like if you had a GPS, which told you where you were and kind of the sort of direction that your destination is, well, then you could just kind of fake it. The details wouldn't matter. You just sort of drive in the direction that your destination is, and hopefully, you can always make progress. So the loop invariant idea is that if you always kind of know where you are and you always make progress, then you'll eventually get there. Now, in reality, you might get into a little cul-de-sac, and you have to sort of come out and fake it. But so I was thinking about loop invariants and whether, all these topics that we've had, whether people really get what we're talking about. I think, people are trying to memorize the steps, and I'm, anyway, so when I was, last night when I was feeling sick and couldn't get to sleep, I was thinking about some examples, and I came up with 2 more pictures that I thought I'd put the board, and then you can tell me whether they're useful or not. All right, so the one idea is if you had some algorithm that had 2 inputs, A and B, and you wanted to add them. And the reason, what I want here is instead of focusing on the action, we want to focus on the state that we're in. So we're going to have 2 variables, x and y, and so the state that we're in will be a point in this grid, right? If I'm sitting here, then the value of x is this, and the value of y is this in our computation, right? And so then one place to start is a loop invariant, and if we use the loop invariant, because that's if we're using a loop invariant like we did for the GCD algorithm. Anybody remember the loop invariant for GCD algorithm? Yes, what?
With modulo? With modulo?
Well, that's... Yeah, so that sounds, if you're saying modular, then it sounds to me like you're asking for an action as opposed to the loop invariant. Right? What is true when we're at the top of the loop? Right, that, we keep having these 2 numbers here. We want to know the GCD of these 2 numbers. The loop invariant was that the x plus y equals a plus b, right? Except GCD, right? So we're gonna keep changing these numbers here, and their sum is the same as the sum of the answer, right? So suppose that this point here is AB, then if we know that the loop invariant is true, anybody know where we are on this graph? You can plot this. The sum of AB, right? This is a constant, right? So the sum is a constant. That's going to be this, right? So the loop invariant says that we're somewhere in this line, right? Everybody follow that? Now then, we want to let's have a post condition. Say the post condition is that x equals a plus b, right? X is our answer. So the post condition, what does the post condition look like? It looks like this, right? You're somewhere in this world here. Right, everybody following that? And so now we want to make progress while maintaining the loop invariant. So if we want to make progress, we want to kind of move in this direction, right? We can't make both x and y small, but we can work on making y small. Right? So what would a step be? A reasonable step? You kind of move in this direction. Right? The easiest way is you make y one smaller and x one bigger. Right? But if you were bold, you could, right? This is kind of where the details doesn't matter. We could make bigger leaps if we were feeling ambitious. Right? So our step is x equals x plus 1 and y equals y minus 1. And what's our exit condition going to be? Right? We're making progress. What's happening as we're making progress? Y is getting smaller, right? So the exit condition is that y equals 0. Right? So what does y equals 0 look like? That looks like this. Right? I guess it goes on further, but so now we can look at the various steps to do an algorithm, right? We have precondition and code A, right? The code before the loop gives us the loop invariant. All right, so we come in, what we have is a value x, a value A and B, and we need to establish the loop invariant. What's the easiest way to do that? Right, the pre-code is that we have values A and B. What should our code be?
A equals x and y equals.
Right? That establishes the loop invariant. And you can see that precondition and the code then gives you, if this is true and this is true, then we have the loop invariance true. Right? Everybody following that? And then we want to say, suppose we're at the top of the loop, and we do the code in the loop, right? And the exit condition is not done. Maybe we should have said that first. And then that gives us, we need that the loop invariant is true after we come around, right? So maybe we make this prime and this double prime. So we can say, let x prime and y prime be the values when we're at the top of the loop, right? And x double prime, y double prime be the values after we've gone around, right? And then what do our things give us? Our loop invariant. What does our loop invariant give us? That x prime plus y prime equals a plus b. And our code, right, gives us that x prime, double prime equals x prime plus 1, and that y double prime equals y prime minus 1. And then you do a little math, and that should give you that x double prime plus y double prime equals a plus b. Everybody gonna follow that? And then, what's our last step that we have to do? Well, the last kind of logical step is we have our loop invariant, and our exit condition gives us the post condition. Right? So you say, loop invariant, what does the loop invariant tell us? X plus y equals a plus b. Right? It tells us that we're somewhere in this line here. And the exit condition tells us that y equals 0. Right? So we're somewhere in this line here. And if both of these things are true, then what follows is that gives us that x equals a plus b. Right? We got, in fact, we got to be right there, which makes the post condition true. Right? And hence post condition. Everybody kind of And then, of course, the only other thing is that you prove that you always make progress, and if you make sufficient progress, then you stop. Right? Did everybody follow that? What do you think of this example? Is it too easy? Too easy. All right. Well, pictorially, right? Got a picture. All right. Well, let me tell you the other thing I was thinking. You can't expect too much from a guy who's sick in the middle of the night. So let's think about greedy algorithms. All right. So a greedy algorithm, I have a list of objects. Object 1, object 2, object 3. Right? And I've sorted them according to some greedy criteria. And for each one, we have to make the decision, right? We have to say, we get to go yes, no, or whatever the decision is. Right? We either keep object 1 or we don't keep object 1. Right? We paint it red or we paint it blue. So that gives us a whole tree of decisions. Right? You can think about it as this decision tree. I start at the top here. I decide whether to say yes or no for object 1. Right? And I decide to say yes or no for object 2. And so forth. Right? Everybody get what this picture is saying? Now, where's a full solution? Right? These leaves here, that's a solution. Right? Because you've made it, the path down makes a decision about every object. Right? Where the algorithm, right? Maybe the algorithm's sitting here because it's only made a few decisions so far. And of course, each solution has a cost associated with it, and some of them, right, are special ones because they're optimal solutions. Now, when we're sitting here, we want a loop invariant to make sure that somehow says we haven't gone wrong. And one loop invariant might say, well, we have a partial cost, right? Maybe it's the sum of these answers, and we have the best answer in this column. Is that a good information? Right? Maybe I'm looking for the shortest path from S to T, and I peg the edge that's cheapest. Right? Is that a good thing to do, to take that first edge out of S that's cheapest? Yeah?
Yes.
Right, let's look at a graph here. Here's S has an edge of 1, it has an edge of 2, and then this is 1,000,000, and this is only 1. You know, which is the shortest path? Right? You know, locally this can look like it's the best thing to do, but you don't know long-term consequences. Right? It's the difference between locally making progress, right? Making decisions based on local information versus the global. Right? So if we're sitting here, we said yes, yes, maybe to the first two objects. And you know what people are tending to do in the test is to say, oh well, the loop invariant says something that we have the best so far, but that's not useful. Right? What is it that we want to be true about this state? What's our loop invariant?
There is a optimal solution in this system we can try.
Right. And what does that look like in terms of this picture?
That solution, we have a solution that we would take this path.
Yeah. Anybody know what this says in terms of this picture?
Somewhere underneath it is an optimal solution.
Right. We look at the tree underneath it, and somewhere in the tree underneath it, there's an optimal solution. Right? Does that make sense? there exists, the algorithm has committed to these two things. It says there exists an optimal solution that's consistent with what the algorithm has done so far. Right? Does that make sense in this picture? And what are we going to call this guy? We have a name that I've been calling it. Who's holding it and what is it called?
Fairy godmother.
Right?
That's called the optimal solution.
Right? It's the optimal solution that we know exists from our loop invariant. The loop invariant says there exists an optimal solution consistent, right? In this subtree, there's an optimal solution somewhere. What about over here? Might there be an optimal solution over here?
Yes.
Is everybody getting this? Yes, right? There may be optimal solutions not consistent with what we've done so far, the algorithm has done so far. That means we burn bridges, right? These would be great optimal solutions. But we can no longer have that optimal solution because we've committed to going this way. Right? And that contradicts these optimal solutions. Does that make sense? All right. So what does the proof look like? How do we maintain the loop invariant, right? Right, so the loop invariant is there exists an optimal solution. Call it optimal solution loop invariant, consistent with what algorithm that's done. Right? So, as we said before, maybe we're sitting right here. This is what the algorithm has done so far. And we know there's some optimal solution down here. Optimal solution loop invariant. Right? Consistent with this. And then the code, we're at the top of the loop. The algorithm is sitting right here. And we know the loop invariant is true. And then what does the code do? Goes around the loop, right? People with me here? People live? You should be at least as enthusiastic as me. Right? Right, so the code, there's two cases. But let's assume the algorithm says yes to what this is. I call this guy object I. All right? Says yes to object I, right? It commits to accepting this object. It commits to painting it red, whatever it's committing to, right? And what does that do? What happens to the algorithm then in this picture? It moves it down here, right? Everybody see that? So now we want to prove the loop invariant. Right? We want to prove that there exists an optimal solution consistent with what the algorithm has done. Right? So what in the picture, what do we want to prove?
The edge OI is
No, because as soon as you say the optimal solution, I get a little nervous because there could be many optimal solutions. What does the loop invariant says? Right? And where is it in this picture? Somewhere in here, right? We want to prove that there exists an optimal solution down here. And what do you think we're going to call this one? Ours. Right? So what we do is we say, okay, fairy godmother, I know that you have an optimal solution consistent with this. Let's call it this. Right? And if it happens to be on this side, right, if it happens to be consistent with what the algorithm just did, then we already have one on this side and we're good. Right? Does that make sense? But if it's not, if it's over on this side, then that's a problem. So we have to take this optimal solution, and we have to give the fairy godmothers instructions on how to change it to create this. Right? Does that make sense? And then we give her, we have a paragraph, a clean paragraph all by itself that says how to tell the, I'm the approver, I tell the fairy godmother how to change this into this. And I say, okay, now you did those operations, now you have it. Right? And then, what do I have to prove about this guy? Three things. I have to prove that it's
Valid.
valid, optimal, consistent. What does consistent mean? That means the previous choices, I didn't mess them up. Going from here to here, I didn't change this and this. I didn't put it way over here. Right? That would be silly. And similarly, I made it consistent with this next step. You know, I moved it from over here to here. I told the fairy godmother, you got to say yes to this object. Right? So, and then I have to make sure it's valid. Well, what does valid mean? Well, whatever, you know, there's some definition of what makes a solution valid. It gives you a path from SCT, it adds up to 92 cents, it doesn't have cycles. Right? I made sure that this was valid, so this is still valid. Right? And how do I prove that this guy's optimum? This was optimum, and this guy's cost value is just as good. Right?
How do you prove the validity?
This guy was valid, and in coming over here, I might have introduced some contradictions, some mistakes, some things to make it invalid, and I fixed them. All right? Does people kind of see this? My biggest problem is I never can hear you.
No, my biggest problem is the validity. Like everything else is going to be straightforward. But, I mean, it's like, it doesn't matter if you can't, the valid.
Right.
Yeah.
Right. Well, actually, of the three, at least one of them is hard, and depending on how you do things, it could be a different one which is hard. Sometimes valid is hard, sometimes optimum is hard.
Yeah, but
Right.
those three are always, that's probably the thing that.
So, should we do a concrete example? Should we do the boxes again, or do you got a different one you want to do?
Okay. If we do the we can do the boxes on whatever anybody wants to, but is it gonna be how hard is the question that you're gonna ask?
It's going to be at least as hard as the boxes.
Sure, let's do boxes.
I mean, they're all, which ones do you think, I think they're all equally the same hardness, right? Actually, the boxes in that one, proving that it's optimum, it had some extra hardnesses in it. It won't be that as hard as that extra hardness on the boxes. All right, so the box problem is we have a set of boxes in the factory, and we got to get them all on the truck, right? If they don't all fit on the truck, then the algorithm's not making a mistake, right? Its goal of the algorithm is to find an ordering of the boxes such that none of them break if there is an ordering, right? Does that make sense? If there's not an ordering, then you can't expect anything from it. And so here's our truck, and the algorithm has put a couple boxes on it already, right? That's because we're down, we chose to put this box on, we chose to put this box on, right? And then the greedy criteria, what does the algorithm do? It finds some box, this is what the algorithm is doing, right? Greedy finds some box, let's call it box I. And what's the property of box I? I mean, it has a weight and it has a capacity, right? But the capacity is big enough that it can hold everybody else. right? If there isn't such a box, we quit. The algorithm quits. But the algorithm says I found such a box, right? So here, I guess we're branching in many ways, depending on which box we take next, right? But we came down here saying we took box I next. Right, everybody with me here? So we're at the top of the loop. The algorithm has done this. Oh, and there exists an optimal solution. Let's draw it here. There exists an optimal solution. Then there's more up there. That's so we say this. Let's do the paragraphs again. We say the algorithm has done this. There exists an optimal solution consistent with what the box has, the algorithm has done, right? So these boxes are the same, and these boxes are the same. The rest can be anything, right? So what we're saying is we're up here, and there exists some optimal solution consistent with these choices. And what is it? It's this. Now it happens in this case maybe that the fairy godmother took box J. She decided to take box J next, right? So there exists an optimal solution consistent with what the algorithm's done so far, and took J, and then there's and then the rest of the boxes are, has box I up there somewhere, has the rest of the boxes. All right, everybody see that? So we say there exists this optimal solution, and then the algorithm takes the next box, right? And then we want to say to the fairy godmother, all right, I'm going to give you instructions of how to massage this guy into this guy, right? This is this, right? And we want to construct this. So what do? Well, the first boxes that the algorithm has taken, we better take them. Why? Because we want to stay in this tree here. We don't want to go way over somewhere else. Right? And then we say, fairy godmother, if you took I next, then we're good to go. Right? But if you didn't, if you took something else, say J, then what do we need? We need I here. Right? Does that make sense? We stick I in. Now you want to say we have to somehow construct the rest of the solution, right? Because we need a full solution. To be a full solution, it needs to have all the boxes on the truck, right? That's the definition of a solution. It has all the boxes on the truck. So we have to put all the boxes on the truck somehow, right? And the one option is we just switch these. We put box J up here, and we leave these remaining boxes the same. Right? Does that make sense? We tell her, just swap box I and box J. So now we want to prove, everybody get the instructions?
The swap.
This was, she had box J here and box I here, and we put box I here and box J here.
But you said that, okay, so if her box I and our box I is the same, then
We're done.
If our box I, if we chose box I and she chose box J, we have to get her to massage hers so that she
Right.
chooses box I.
Right.
And then we're swapping what she had originally
Right.
with something that she chooses later on down the line. Or
Don't get to this, she chooses down the line. It's here, it's concrete, it's there. Right?
Okay.
She's holding it.
Okay, so
Right? So we say, one way we can get instructions is simply swap your box I and your box J. Right? Does that make sense?
So our
Yeah, and then that gives us this thing. Right? That gives us this optimal
consistent
solution.
with
ours.
her.
Well, now what do we want to prove? Is it consistent with what the algorithm did in the past? Yes. Is it consistent with the algorithm just did? Yes. So it's consistent with the algorithm. And that's good. Right? Is it optimum? Is it optimum? Well, we didn't have a sense of optimum. It either takes all the boxes or it doesn't. Right? So it's taking all the boxes. Is it valid? What does valid mean in this case? Does any box break? Right? Do you see any box that it's in danger of breaking? Box I?
No.
How do we know box I won't break?
Because the algorithm chose box I.
Right, because it can hold the rest. How do we know these boxes don't break? Is because they're holding the same things. Right?
So then why did the fairy godmother put the box I all the way up there if they didn't?
She decided she wanted to do that.
But wouldn't a box break somewhere there?
She told us that this is a solution. Right? We had to trust her.
If you put the J at the top, because the box standing at the I, it can just break. Because the J is much heavier.
Right, so this box right here,
Yeah,
what happens if box J is heavier than box I?
or it can break.
Then this box can break. Right? Does that make sense? So this is a bad method. So what do we do instead? Is we put the box J here, the I here, and we just shifted everybody else up. Right? So this is box J, and then these ones are straight across. Right? We took box I out, we slipped it in here, and everybody got shifted up. Right? That's a different instruction for the fairy godmother. I just gave you the instruction to show you how things can go wrong. Right? Now we want to prove that nobody breaks. These lower guys, they didn't break here. Right? I, we know, doesn't break because it can hold everybody. What about box J? It didn't break here. It has the same stuff on it minus I. Right? So it's not going to break now. What about all these guys up here? These guys, again, they're the same, have the same stuff on them minus I. So they're not going to break. And the guys above I have the exact same stuff on them. They didn't break here, they're not going to break here.
But how do we know? Like, we're still assuming that the fairy godmother the box changes.
Right. So this goes back to what are we trying to prove? We're trying to prove if the loop invariant's true and the code selects the next box I, then the loop invariant is true. Right? So we assume the loop invariant is true. We assume the code happened. The loop invariance tells us that there exists an optimal solution consistent with everything up to here. And there it is. Here it is. We assume that it's a valid optimal solution. So we have that. Right? And we use that to prove that there's an optimal solution consistent with what the algorithm had done before and what it did in this last step. Does that make sense? And when we're trying to the last question was about optimizing, and it was definitely a little trickier. But you just note that things get better for every box, right? Except for box I, it gets worse for, but it had the best W plus C value, so that doesn't cause us problems. But let's not worry about that one. Very good.
就说你如果说也是可以的，但是在这里应该就是
Yes.
在这里多说，对，在这所有地方。
Yes. Then, does the greedy algorithm work?
那么底下项目就
No. We proved in test 5, question A-ish, that it doesn't work.
好的 solution 上不是 optimal。
Yeah, the greedy algorithm only
自
works
己的跟
when you do take all the
把
boxes.
它的 J 放在自己的 I 上。哦，有点明白。原来是这样。
Solution you say that box I is over J, right? So when you switch it in, like when you put J on top of I, like doesn't
现在才
is
明
there a
白。
possibility that it will break?
That I will break? No, it's a good question, but the reason we have to, at some point, you also have to use the fact that the algorithm chose the box, right? Why did the algorithm put this box here? Is because by the greedy condition, it's able to hold the rest of the boxes, right? The algorithm says some box has to go here, and it's a box that holds the rest of the boxes. So if there's not such a box, then the algorithm will quit, right? But it said, no, there is a box, it can hold the rest. So that's why we didn't worry about bringing it down, because we know it can hold the rest. Any other questions? How are you guys feeling about these various things? You think you can do a greedy algorithm? You think you can do a dynamic programming algorithm? Loop invariant question? Recursion question? Math, those math questions, they're just memorize the table, you know, let's not panic about those. First order logic is kind of hard. I bet you if I put a good hard first order logic question, you'd all get it wrong. But, you know, same for the grad course.
Are we still having network flows?
Yeah, everything that we taught can be on the course, on the exam, right? So, I talked at one point about the types of questions that were on the exam before, right? The types of questions where I give you a network with a current flow, and then you're supposed to get the next flow. And how do you do that? You build an augmentation graph. You look for a path through the augmentation graph. You augment it. You get a new flow, right? And then I probably ask you to do it again, right? You have this new flow. You build a new augmentation graph. You say, oh, look it. There's no path from S to T. So I stop, right? And then I ask, how do you know that this flow is optimum, right? And what do you guys say?
Because you can't go do it.
Yeah, that's what half of you say, that the reason that we know it's optimal is because the algorithm stopped. And the reason the algorithm stopped is because there was no path in the augmentation graph. But that's not a proof to me, right? You have to, for that to be a proof, you have to rely on the fact that we proved that the algorithm works. Right? So how do you know that this is the maximum flow?
If it was max flow,
What?
if it was better flow, you would have gotten it from the augmentation graph.
Yeah, that's not necessarily true, right? Because there could be a local maximum. How do you know that there's not a local maximum? How do you know that yes, I'm stuck in a local maximum, that there's not a global maximum somewhere? The cut, right? When you look for the path from S to T, everybody reachable from S gets put into U, everybody not reachable from S gets put into V, and that's a cut. And you note, look at, the value of the cut is equal to the value of the flow. And clearly, you can't get any more flow from S to T than the amount across this cut. So the cut is a witness that you can't get a better flow. The flow is a witness that you can get this amount of flow, and the cut's a witness that you can't get a better flow. All right? So that's if you answered because there's not a ST path, you'll get a good goose egg. If you answer, oh, I have this cut and it matches and it's a witness the fact that there's not a better flow, then you'll get perfect on that part. Right? I mean, I've given you all the answers, right? So all you have to do is write them down.
Could we have a lot of pictures on the test expense?
Pictures? Am I going to draw pictures?
Yeah.
I must admit, I've been so enthused I haven't even made it to the exam yet. But, pictures are good. Pictures help? The pictures of the boxes on the truck?
That one, the last one did, but none of the video.
Yeah, the video was completely
Yeah.
until you started writing the code.
Right. I don't know if I haven't had a picture then. Oh yeah, you had the modifying picture.
This one.
That picture, I had that picture on. Yeah, I thought that picture would have helped.
It helped like while writing it. Maybe after writing the code. Are you gonna hold our hand to it like you do for these ones, like part A, B, C?
We're gonna do less of that. Why? Because you've been spending 2 hours per unit test, right? There were 5 unit tests. You have spent 10 hours writing tests already, right? And I've spent I don't know how many hours marking them, right? So, I mean, one question is, do you think it was worth doing all those hours? Did you?
Yeah.
All right, so on the exam, I got it confirmed by the powers to be that our exam is from 9, 10, 11, right? 9 to 12, right? And there's not another exam until 2. So that means we can stay there until 12:30, and hopefully nobody bothers us. Not 12:30, 1:30. We can stay there until 1:30 and nobody will bother us. So that gives you 4.5 hours, which is just a shy shad of 10. If you know what I'm saying. Right? So there's two issues here. One, I'll give less part questions, and 2, you'll have to do each question faster. Right? For 1, don't copy out the question. Just get in there, give me what I want. Right? Give me as many details. In fact, let me tell you, if you haven't figured this out already in your life, something that you absolutely have to do in every test is you have to say, at the very beginning, you get your test, you say, how many minutes do we have? Right? And how many minutes per mark? And now this question's worth 8 marks. How many minutes is it worth? Right? And do not spend more than that many minutes on that question. I mean, what I did in the past is I did the math for you. In fact, I wrote next to each question, this question's worth 8 marks, hence it's worth 20 minutes, or whatever the math works out to. And maybe I'll try to, it's a bit of a pain to do it for myself, but it saves you all from doing it. And then you get everybody come with a watch. Right? If I have, hopefully I'll be able to project it on the board. And then you watch. You make sure you don't spend more than that minutes on. And you start with, what are the key things I need to get down in order to make Jeff as happy as possible in those minutes that I have? Right? I want to see evidence that you understand the steps. I want to see evidence that you translated the steps as much as humanly possible into the question at hand. Right? And you have to do it fast. The other thing, I must admit, I don't know how this will help you think about the exam, but I'm feeling very unenthused. And my sister I haven't seen in a year and a half, and she's arriving the day before the exam. So I don't want to spend a lot of time marking. Right? So I'm going to try to have questions where, if you all could do me a favor and write correct answers, because they're much faster to mark.
Is there going to be an art therapy question?
Yeah, I love art therapy questions, I get a sense of how you guys are doing, and, we had a few more hangings on the last test.
You like my trunk with a funeral?
Can you show up early to doing the test?
That's another thing we can discuss. I'm willing to come once more before the... Oh, you mean actually on the test have longer hours? I suppose. I didn't ask what time the janitor comes, right? So it's possible we'll come and the place is closed. How many people would want more hours and would want me to show up early? How early are we talking?
8.
Show up at 8? You know, it takes me an hour to get here. It means waking up at 6. But, I suppose.
And make it easier for you to mark.
No, because the more shit you write, the more hours you have, the more shit you write. Actually, you will feel rushed. So, I find what people do is they barely read the question, and then they start writing shit. Right? Blah, 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 blah. And you can tell that at some point their brain turns on, and they start writing good things. Right? Often that shit is a repeat of the question. Right? So just don't. Right? Don't write. What you do is you read the question, you read the question, you read the question again. In fact, I have to tell my son Josh, almost every question he gets wrong on tests is because he didn't read the question. Right? Read the question. Right? Think. What is the instances? What are the solutions? What are the costs of the solutions? What are the various? Think about the question, and then think about the main steps in the. Think through a bit. Think what would the bird ask? What would the sub-instances be? Think about it before you write anything down. Right? If this is a greedy algorithm, let's have a commitment here. For the dynamic programming algorithm, do not write anything until you know what the instances are, what the solutions are, what the costs are, what the bird's going to ask, what your set of sub-instances are going to be. Right? You have that kind of worked out in your brain, spend 5 minutes doing it, and then you can just write the code down. Right? You have the table, say something about base cases, loop through the sub-instances, make sure I know what sub-instance we're talking about, loop through the bird answers, make sure I know what bird answers you're having. Look, who's your friend, and how do you look it up in the table? How do you construct your cost from it? Right? Take the best of the best. Just write it down. You can do it fast. Another thing I must confess that makes my marking easier is I don't have to make comments. Right? No, it doesn't look right.
This may seem like a cop-out, but it seems to me that quite often with the questions on your test, I spend a lot more time trying to figure out what it is you want than it is actually writing down the answer. Is it a case that I need to be creative? Or are you testing me on my creativity to figure out the answer, or am I being tested on writing out the steps? You know what I mean?
Right. Well, I'll own some of that, right? I try to come up with new questions because I have fear that the questions are out there. And it's hard to come up with new questions. And it's hard to come up with questions that don't look too easy. Like I did that loop invariant one. Yeah, it was easy, but I find there's some that are easy, that are so easy that you think, this is wrong, right? And it kills you. And there's ones which then you don't quite understand the question, right? I try to explain the question, right? You have boxes, we want to stack them. Right, the one example which was definitely what you're saying is absolutely true was the games. Right, the game one.
Please don't put anything
That was
close to that.
Well, maybe we should cover it right now. Could you do the game one if I gave it to you right now?
Yeah.
I think you should, it's a classic thing. You should know how one decides whether a state of a game is a winning state or a losing state.
No, I don't understand that. Can you explain the game question?
All right, let's do the game question.
Yes. I totally confused about the game
I think
question.
it's a good question, first.
Yeah. When you said repeating questions, what about postcondition, precondition? Sometimes you write that. Do you still want us to write that in our answer? Precondition, postcondition?
No, because it's up there. It's up there. Now where I would want it, if you say loop invariant and exit gives you post condition, right? Then you say, what's the loop invariant give me? Well, right, real quick, right? What does the exit condition give me? Real quick. What does that give me? That write down the post condition, hence the post condition, right? I mean, at some point I have to make sure you read the question, but
You don't need it late.
I don't need it at the top.
Cool.
All right, so
它不需要什么的套，就是 post 可能写了你就不要写，浪费时间。就是它简单的东西写不出来就别写，别浪费他的时间。这道题他给我们那时候有讲义，走了，给我们讲，清楚是不是清楚？他是要从底开始做，往前做，他不是从上面往下走，是从下面往上走，倒过来。你怎么确定他从底下往上？他说的。你只有确定了下面的路，才能知道上面是什么，赢的还是输的。IT 是啥？IT 不知道啊？是什么意思？这老头很厉害，后面那个老头很厉害。
all right, so
I also know one's turn go to the one's turn.
oh, you're right. I didn't think of that when I was making up this example. Let's say that the game is you draw a card and you get an extra turn.
Sometimes.
Sometimes. All right. So he's absolutely right. So suppose each dot here is the state of the game, right? It tells you where all the pieces are. It tells you what's in your hand. It tells you everything about the state of the game. And one of the things about the state of the game tells you whose turn it is. And he was complaining, that it's one's turn, and then it's one's turn again. But that's because he laid what did he do in this turn? He laid a card that said, I get another turn. All right? That's a cheat, but, I'm not in the mood for making up another example. All right, everybody kind of get that?
I can't see. She's
Get your head out of the way, buddy. All right, so this here, 0 wins. Here 1 wins. Here 0 wins. Right? So the loop invariant. This is a loop invariant question. The loop invariant is everything that we've done so far. Everything, what we want to mark every state with is either 0 will win if 0 plays a good game, 1 will win if 1 plays a good game, or they'll be in a stalemate forever if they both play a good game, right? So far, the loop invariant is true because all that we've labeled is here, 0 definitely wins, 1 definitely wins, 0 definitely wins, all right? And all we're going to do is we're going to play just like you do in this thing, whatever this is called. You fill in the boxes, right? If you know a number goes there, you put it there. All right, so let's look at this guy. It's 0's turn. 0 could either come down here and win, or he could come down here and lose. Which one do you think he's going to do?
Down there.
He's going to come down here and he's going to win. So what's he going to do? He's going to win, right? And now it's 1's turn. 1 could come down here and lose, or come down here and lose. What's he going to do? He's going to lose, right? So who wins? 0 wins. This guy here is 1's turn. He can come down here and win, or he can come down here and lose. What does he do? He wins, right? So you keep, whenever you can see that you can fill in something, you fill it in. Yeah?
How do you know he won't make a mistake?
Well, we're always assuming that they're brilliant players. All right? That's it. What we're saying is we label it 0, meaning if he does the right thing, he will win. Right? If he's dumb, he will lose. Right? You know, you can always lose if you're sufficiently dumb. All right? So what is our step? Our step is, if it's my turn and I can move to a spot where I win, then label it win. Right? And if it's my turn and everywhere I go, it labels that I lose, then I lose. Right? Now, can we label this guy? He can come down here and he can lose, or he can come over here, which we haven't labeled yet. So we can't label yet. What about this guy? He could come down here and lose, or he could come down here, which we haven't labeled. Right? This guy here can come and lose, or he can come, which you haven't labeled. This one could come down here and lose, or we haven't labeled. Everybody kind of see the pattern here? This one here, he could come down here and lose, or he can come over here. We haven't labeled it yet. Right? Everybody see that? Is there anything we can label? No, there's nothing we can label. So what should we do now? We call them all stalemates. Right? And you can do a formal proof of it, but you can think, if it's this guy, what's his choice? He could lose, or he could stalemate. He'd rather stalemate. Right? What's this guy? He could lose, or he could stalemate. Right? Each case, they could lose, or they could stalemate. Right? So how do we know that everybody that we've labeled stalemate, he will stalemate? Well, if he could win, we would have labeled it. Right? If he was guaranteed to lose, because they all go to a lose, we would have labeled it. Why didn't we label it? It's because they were all to losing, except there was at least one to a I don't know. Right? And that I don't know turned into a stalemate. So now he can either lose or he can stalemate. And that's the entire thing.
How do you ever win? How do you ever win?
I make a mistake.
I just made this example up, sitting right here. That's not the best example.
Make a big mistake, right? That's how you would lose.
Yeah, you make a mistake by losing, right? Or we can put in another guy here. It's Zero's turn, and Zero can, he could stalemate if he wanted to, but he would rather win. Everybody kind of get this? So it's the loop invariance is the most simple kind, which is you only fill in things, and that's if you know that they're right. So you're maintaining the loop invariant that everything you've done so far is right. And then the hard part was that the loop invariant says everything labeled so far is right. The exit condition says I don't know how to label anybody else, and so then the post condition you prove that everybody labeled stalemate is in fact stalemated. Does that make sense? What about that question now? Could you do that question?
I think so.
How do you do this algorithmic? How do you actually check those nodes? Stalemate.
Well, on the test I had another question. What data structure would you use? And I would put all the nodes that I haven't labeled into a heap. Right? And what I want is if I can label them, then I want them to pop to the top of the heap. So what would their priority be? Well, if they can move to a win, then they pop right to the top. Otherwise, it'll be sort of the number of ways in which they lose, and or maybe the number of things that are unlabeled yet. And when there's nothing labeled anymore, then they pop to the top, in which case you can make them lose. You have some sort of data structure. Or you do what you do in this is, you just keep going through and say, hey, where can I put a number? You search around it. Oh, I can put a number here. What? Mark them all X? Yeah, S, exactly. That's what we should do here. I'm stuck. Yeah?
Do you have the lecture videos that somebody posted on the
He's the man.